You're going to share content from the section.
Okay.
So now you're running Zoom from here.
Okay.
If you want to go back into your PowerPoint, you can also share that content.
Okay. Okay, sounds good. Hopefully, it can start.
So it seems to me like the mouse and the keyboard is going to do. That's not great. But
Yeah, let's just keep it at outcome for now. Probably that's the best to not wasting a student and in pension now already. Let's just go with that. Okay.
This is the same thing.
Okay.
Like the students on Zoom can see it, and the students in the classroom can see it.
Okay.
So it's
just can you go back?
let's do that. Just let's leave it how you asked for it.
Okay.
We'll get at it.
Yeah, thank you. I'm really sorry about that, but let's, I'm hoping that today give you guys really good idea on the diodes, and of course we have 2 more lectures. And usually for this class, if you notice that I'm covering the primary sections, the last 1 or 2 sections we usually don't cover because they go a little bit depth. And then also our exam also only covers up to the point that we covered in the class, and the homeworks too also cover to that point. And then the last lecture, usually I give a lot of examples from the book that you guys can take it. So for diode, as you learned last time, it's the symbol for a diode, and usually we use D as a symbol for diode. And in this class, we're going to have 3 types of model. When you apply a voltage, you will have current flow through the diode. And the relation between the VD, you look at the VD, how we draw it, it's a positive connect to the P side of the diode. The diode is just a PN junction, nothing else, nothing special. And the relation between VD and ID as I mentioned, we have 3 different type of models. Now you might question, why do you have 3 models? Well, those models are purposely built for different purpose. When you want to have a quick, high level look at the diode, see what happens, and we use a so-called ideal diode. So in the ideal diode, the current look like this. So what it does say is that ID can be anything if VD is larger than 0, and ID is 0 if VD is less than 0. So that one is called, so number 1 is ideal diode. That's an ideal diode. And this happens is, when, as I said, we use this model for high-level analysis of a circuit, and also for digital circuits. In digital circuits, we count either 1 or 0. And that 1 means high voltage, that 0 means low voltage. So for high voltage, whether it's 2 volts, 3 volts, or 4 volts, 5 volts, it doesn't matter. It just indicates a high voltage. So if it's 5 volts minus something, 0.1 or 0.7, it doesn't matter. It's still 4.7. It's still considered as a high voltage. So we represent as 1. So this is very popular when you start to learn diodes. But then we move on to a second model, as we call linear piecewise linear model. Piecewise linear model. In this piecewise linear model, the diode is no longer ideal, but it's like this. So the thick line that I draw is the current, and then the horizontal line is voltage. So in this line, you can see the difference between this one. The ideal model is that when VD is less than 0.7 volts or less than 0.7 volts, ID is 0. But when VD is larger than 0.7, ID can be anything. So it can be anything means we don't know how much it is. We have to calculate ID based on other components in the circuit. So if you don't have any other components in the circuit, this circuit will have an error, so it doesn't work. Like in this case, for example, the one that I draw in the beginning like that circuit would actually not work. You either don't have current or you would burn the current. You wouldn't burn the diode because that current will go infinity because there's nothing to limit the current. So, so this is the second model. I'm going to go through examples for each of this model. And then the last one is called nonlinear model, or sometimes called a real diode. It's like a real, in the real world, what would be a diode look like? And this line of the current will go like this. So which means current is not exactly 0 when the voltage is less than 0.7, but it is close to 0, but small. But when it approaches 0.7, the current will start to increase, but it's not infinity. It will increase by dramatically. So this line here is 0.7 volts, and here is 0.7 volts. So that's 0.7 volts. So you see that current will go quite big at that direction. So now, given the three models, you might wonder, so going to the exam or doing a design project, or I'm going to design something for myself, which model do I use? So again, it depends on the application. So if it's a digital circuit, you're definitely going to use the ideal model. So did I say here? So I write down. So this is ideal model. Now, if you're going to do some other circuits, not digital, but you want it to be more realistic, then the ideal model, you use the second one called piecewise linear model. But you want a more like nonlinear performance. You want real like exact performance of diode. You don't want to get any error of your result from a simulation or something compared to the real world application, to the model that you have in your simulation program. You want to use the last one. It's called nonlinear model, sometimes called the real diode. So let's start with this ideal model and to see how you would work on different things. So let's say you have a diode. Yeah. The current, if you connect a 0.7 volt or larger to the diode without any other circuit, the current will go to infinity because nothing limits the current. So that's why you're going to see a circuit that I just always have some resistance connected to the circuit. So let's see. So if it's an ideal model, let's say this is 10K. You guys can do it together. How much you think ID would be in this circuit if it's an ideal model? Because in the ideal model, we have the diode drop at 0, the voltage is 0. So here, from here to here, it's 0. So therefore, our current is basically 10 volts minus 0 divided by 10K. That gives you 1 milliamps. Now, if I have a circuit in this case, what do you think the current would be? Because the diode blocks current going through the negative to the positive terminal. So therefore, in this case, your ID will be 0 volts. 0 volts. So that's for ideal model. Now let's move on to talk about the linear, the piecewise linear model. So for the piecewise linear model, we're going to do it here. Okay. So you have the same circuit. So you have VD at 0.7 is drop. So therefore, you would have a current of 10 minus 0.7 divided by 10K. That gives you 0.93 milliamps. And for the second circuit down here, same thing, you have VD 0. Again, the same circuit, you have this one. For the ideal model, you have 0 drop. But for the piecewise linear model, you have 0.7 volts drop on the diode. So if we can write it down here is that VD is 0, and here VD is 0.7. So those are fairly easy. When you guys go through a lot of exercise in the problems, you'll find it's very easy to do. Whether it's a linear model, whether it's an ideal model, you simply take the voltage drop. If it's an ideal model, no voltage drop. If the piecewise linear model, you reduce 0.7 volts for each diode. You have multiple diodes in series, reduce 0.7 for each diode that are connected. And if the voltage in the reverse direction, there's no current. Right? So fairly easy to do. But let's move on to the last one. Last one is nonlinear model. For the nonlinear model, apparently we can no longer say, well, what is the voltage of VD and ID, so on. So in theory, we call this one, we have what we call a SPICE model. So you guys probably already familiar with the SPICE model simulations. When you do the project, you had a lecture last week about simulations, whether you're going to use P-SPICE or LT-SPICE or Cadence, they all use SPICE model. So SPICE model is the one that built in the simulation package. It reflects the real performance of diode. Of course, it's not 100% because what we are doing is we want to use physics to explain the performance of semiconductor. I mean, you can never be 100% accurate, but this very realistic. I would say 99.99% accurate to describe a diode in a SPICE model. So in the SPICE model, you will have ID equal to IS e to the power VD over VT. So here VT is called a thermal voltage. This IS sometimes called a saturation current, sometimes called something else, that a few different names for that. So it's okay. This one is typically IS is in like 10 to the negative 10, 10 to the negative 15 or something like that. And VT 25 millivolts is called thermal voltage. Now, when you guys do diodes calculation, there's one mistake a lot of students will make in the beginning is that they forgot the unit. So they would simply plug in 25 instead of 25 milli. 25 milli is 0.025. So if you plug in 0.025 to that equation, you'll get everything right. You plug in 25 instead of 0.025, you will see that your current is messed up. It almost is error by 1,000 times, or maybe even more, because it's e to the power of something. So that number becomes really small. But if you wait till 0.025, and then everything's right. Okay, so for here, you will often meet this concept saying a diode has this property of 0.7 volts at 1 milliamps or something else. But this is a very popular term saying, what did it say that? It said that this diode is a non-ideal diode. If you apply 0.7 volts exactly at the terminal, you will get 1 milliamps. But if you apply, say, more than 0.7, you can imagine what happens. Current will be more because look at that equation, VT over VT. So when VT is 0.7, you got 1 milliamp. So when VT is more than 0.7, you will get more than 1 milliamps. But when VT is less than 0.7, you will get less than 1 milliamps. So it's really this equation, this diagram on the top, you can see that's the area that the current would follow, okay? Now, what happens to the negative part? Well, the negative part means generally there's no current when you apply negative voltage on the diode. But if you apply too much voltage, what happens? The PN junction breaks down because the PN junction is a physical connection. It can only withhold certain voltage. If voltage is more than certain volts, it's going to break down. When it breaks down, it can flow a lot of current. So that's where you see the current start to increase dramatically. And for normal diode, if you do that, the diode is down. You cannot use it anymore. It's breaking down. It's burned. Okay, it's because the current is so big, it will generate heat, and the heat will actually burn the PN junction. The whole diode is dead. So don't do that. But if it's a Zener diode, that's a different story. So that's built in a different technology, and it will allow the diode to break down, but still maintain certain current and voltage. So that is where this voltage over here indicate the breakdown voltage, and you can flow certain amount of current, and the diode will still work. And if you remove the voltage, the diode becomes normal. So a Zener diode in the positive direction, it works just like a diode. But in the negative direction, it works like a voltage stabilizing a certain voltage. Okay, so we're going to get to that in the last lecture. So now you have all three models. We can go through. Let me see. To do a few example circuit. Let's say you have a circuit, then we have AC input. So what we have is this is well, let's call it VI, and you can see the diode is in the let's call this 2K, just a random number, for example. Let's say this VI has a waveform of this. Let me draw it over here just for comparison. So let's say we have VI is a sinusoidal waveform. Because the diode is going to block the negative voltage, so when voltage is positive, you can see current would flow from voltage source through the two resistance, through the diode, it forms a current. So you have a current going through this way. But when the voltage is negative, so what happens? The diode will block any current to go through. So there's no current. So in that case, I want to see what voltage would you see over here? Let's call it VO. So what voltage do you think would form at the 2K resistance? I'm going to draw like a few possible scenarios that you guys decide which one is correct. So I'm going to draw one over here. Oh, let's say this voltage has like 10 volts, and the negative also has minus 10 volts. I'm going to draw it like this, 10 volts. Okay, so I'm going to draw another one. I'm just going to draw randomly 10 volts. I'm going to draw another one. So I'm going to here is called ideal diode. So for this one is ideal. Ideal means the voltage across the diode, when it's in positive, when it's in forward direction, is 0. So voltage is 0. So among those 3 different curves, which one do you guys think will be? What? I have 3. One. Why this one is not correct? Well, you guys select number 3, that is correct. Why? Because when the diode is conducting, the diode like a short circuit, and you have 2 resistors in series. When you have two resistors in series, they are in a voltage divider. So you're dividing the voltage between a 1K and 2K. You have 10 volts, right? So that 2K will have 6.7, the other one will have 3.3. So that's why number 3 is correct. So you guys saying, okay, so last one is correct. Yeah, so we're going to leave that one. So this one is correct. But only that 6.7 volts is like sinusoidal waveform. And the negative half of the voltage, we don't see anything. We don't see anything because the diode would not let current to flow in the circuit. It would not let current flow in the circuit in the negative half of the voltage. So I pose a question for you guys. If it's in negative half, there's no current flow, the VO is 0. But we do have a 10 volts input or assigned input on the input side. What happens to that voltage? Where does that voltage go? If we do a loop analysis, you would have, right? So if no current, which means the voltage drop on the 1K, the voltage drop on the 2K, they're both 0 because no current. So no current times resistance is voltage, right? But you have 10 volts input. So where would you get the voltage equation balanced? Where did that voltage go? Well, we can write the equation like this. So basically, 0 current, 0 volts, 0 volts. This is minus 10 volts here. So what do you think if we measure the voltage from here to here? How much would you get? If we measure the voltage across this diode, negative to positive. Use loop analysis, this 10 volts, add it together. I probably shouldn't have the negative sign because that voltage is actually already put in the negative direction. See, the voltage over here, the whole circuit, you add all the voltage together, you get 0, which means if you have 10 volts here, you got to have a 10 volts over there. So VD is actually 10 volts. So in this case, your VD is 10 volts. Okay. All right, so now we have this ideal diode. Now, if it's not an ideal diode, if it's a piecewise linear model, what do you think about the output voltage? So if it's piecewise linear model, that VD will become, in the positive, will become 0.7 volts, right? So then your output waveform will become here. The peak is going to be 0.7 less than the input. So this becomes 9.3 volts. Well, not 9.3, 6.2, because the two voltages, two resistance dividing that 9.3 volts. It's piecewise linear mode. If it's a non-ideal diode, in this case, it's a little bit complex. We're going to leave this to our next lecture to talk about it. But let me start another circuit. Let's say we have a voltage source, and then we're going to have this. I'm going to have diode over here. we're going to have R, V, and we're going to have, what we call this? Vx. Okay, so in this case, we have V equal to, say, 15 sine omega t. That omega can be in any frequency, but we have Vx equal to 12 volts. And again, ideal diode. So which means if we draw Vi, it's going to look like this, where the peak is 15 volts. So now we want to draw VO, let's call it. Well, let me do this, not VO. I want to draw ID in the circuit. Let me give some value for R. Let's call R is 1K. Make it easier, so 1K. So we have 15 volts input AC. We have diode and we have resistance 1K, which is before the diode, or you can put it after the diode, doesn't matter, the circuit wouldn't change. But we do have a Vx at the output side on the right hand, which is 12 volts. So when you look at this, what happens when Vx is less than 12 volts? Not Vx, Vi, sorry. Vi. Vx is the other side. So what I meant is when Vi is less than Vx, which means the diode will see we're not going to see a positive voltage drop. It's going to, so in any case, when you have a diode, the positive and negative between those two, you got to see in the beginning, at least you have a positive voltage for it to conduct. When conduct, you can say the voltage is 0. So when the input voltage is less than 12, apparently it's going to be less than 12 on the right hand. So therefore, the current is 0. So when Vi is larger than 12 volts, what is the current? Well, we can write current as Vi minus Vd minus Vx divided by R, which in this case Vi is 15 times sine omega t minus Vx is 12 divided by R, which is in this case is 1K. Well, you can see already this current has two terms. So one is a sinusoidal current, and another one is 12, but the 12 is minus. So therefore, really what you're doing is here. So if this is 12 volts, about 12, you're going to have a current. But if it's less than 12, there's no current. So it's just a little bit current at this point. So that's the sine wave minus 12. So what we are doing is simply shifting that sine waveform over there, down, all the way to here. And what's the peak over here? Can you guys tell me? For ideal diode? So the peak is 15 for the Vi, minus 12, divided by 1K. See, yes, you have 3 milliamps. So that's your current at the diode, through the diode, okay? So this is, okay. Mini circuits, let's see. Okay, so I think we're gonna, okay, well, we have to erase this one and start a new diagram. So now let's move on to look at some examples. So this example, So again, this is what we're talking about is ideal diode. Okay. Now, as you can see, we start from easy to more difficult ones. So just get step by step getting into the problem. Now, this circuit apparently is a little bit more complex than the circuit we had before. So you have like two voltages, one above and one below, and you have two diodes. And the two diodes, not in parallel, not in series, they're actually in two different branches. So in theory, this circuit, like how many we want to say to have nodal analysis or loop analysis, as I mentioned before, nodal analysis is most preferred in electronics because it's just a bit easier. You solve less number of equations. So in this case, how many nodes do you have, or do we have? Just one, yeah, just one. Because that voltage, apparently they're not nodes, right? You basically can have, if you want to draw the complete circuit, you can certainly draw the voltage source and connect to ground and so on. So we really have one node. So we really have one node. When you get to more than one diode, later on you're going to see like some circuits have 3, 4, 5, 6 diodes. Sometimes very difficult to know where to start, and sometimes it's just hard to calculate the results without knowing which diode is conducting which diode is reverse biased. So in that case, all you need to do, you have to assume, you have to make an assumption. So you make an assumption saying, okay, I'm going to assume this diode is conducting or forward, and I'm going to solve the circuit. So once you solve the circuit, you'll go back saying, well, did I make it right? Like if you're in positive conducting, but later on you find the voltage across the diode is negative 5 volts. Apparently something is wrong. So you have to go back. Well, that's not possible. So it must be reverse biased. Okay. So let's call it D1 and D2, and we'll start looking at what happens. Because when you make a different assumption, that circuit changes dramatically. So our step one, we're going to assume D1 forward. Now, I'm interchangeably using like forward conducting and so on, and sometimes, so it's the same thing. And I'm not called like reverse biased or like not conducting or off, like they all mean the same thing. So forward means on, it also means conducting, it's all the same thing. But if you, later on, we're gonna assume like reverse biased, off, not conducting, they mean the same thing, okay? So we're gonna use all this. So let's say if it's an ideal diode, we assume D1 is forward biased. So if we assume D1 is forward biased or it's conducting, what would be the voltage you get at the node? Let's call this VO. 0, right? So if we do that, we're going to say VO is 0 volts. So if VO is 0 volts, we can start to calculate current. Let's call it I1 and current I2. So we can count I1 will be 3 volts minus 0 divided by 12K. That gives you how much? 0.25 milliamps, right? So we're going to calculate I2, which is 0 minus divided by 6K. That gives you 0.5 milliamps. So what we are saying is I1 is 0.25 and I2 is 0.5, and D1 is forward biased. So without a further explanation, can you guys tell me, is it possible? Somebody said no, why not? Yeah, so I2 is larger than I1 means some current has to come from in the reverse direction. But we said actually cannot up, but actually forward bias, which means it has current, supposed to have current going in. Is wrong. So assumption is wrong. You see what I mean? So often, when you make an assumption, you have to go back check whether you made it the right assumption or wrong assumption, because that might just not right. So in this case, which means we have to go on to assume D1 reverse, or reverse biased off. As I said, it's the same thing. So if we assume D1 is reverse biased, what is voltage now? We all, do we know? Okay, you had a question? What is it? Oh, why not? Then I1. Well, yeah, so where do you get the difference? So I1 is flowing down, right? So I2 cannot be large more than I1. If it's more than I1, you don't have a current coming, so you don't get, yeah, so that has to be wrong. So now, if I assume D1 is off, or D1 is reverse biased, which means there's no current, can you tell VO right away? Can you say what VO is? Can you say 3 or -3 or some or 0? Can you say that? No, no, you cannot say that, because we really don't know, because when D1 is biased, you can draw reverse biased, you can draw an equivalent circuit like this. Because there's no current, we'll simply have that circuit open. So in this case, because D1 is reverse biased, we have there's 3 volts here. Zero current here. Of I, which in this case is okay, let's do it this way. So it's I1 is I2 is the same, which is equal to 3 minus 3 divided by 12K plus 6K. So it's 9 volts or 6 volts divided by 18K. That gives you 0.33 milliamps. So from here, we can see VO is 3 minus I1 times 12K. So you see, I want to find VO here. So I have 3 minus I times 12. That gives you 3 minus I 0.33 times 12. How much that gives you? So it looks like it's minus, is it -1? Yeah, it's -1 volt. But at this point, some students in the past students started to question, how can you have a negative voltage? What you're looking at is negative. What you're looking at is whether the voltage on the positive side is higher than the negative side. As long cannot happen this way. So this is very very simple. Okay, let's see what happened to mine. Everything's not working today. I don't know why. Okay. Yeah. So this is, let me see. Okay. So what we're going to do is for the same circuit, but I'm going to change the value to, I'm going to change this to 6K, this 12K. So I'm going to flip the two resistance to look at what happens with each, with this circuit. So instead of, now the top is 6K, the bottom is 12K. So we're going to do the same assumption, see what happens. So we're going to assume D1 conducting or D1 forward. So we assume that we're going to get this VO. We get VO 0 volts. So now we're going to calculate I1 and I2, see what happens. So we're going to get I1 is 3 minus 0 divided by 6K and gives you 0.5 milliamps. We get I2 equal to 0 minus 0.25 milliamps. So you might say, well, the two currents are still not the same. With it, let's look at the circuit in detail. Is it possible or is it okay? Yes. Why? So I2 is smaller than I1. Okay. And then where is that difference go?
I1 plus I2 smaller, so you take the difference, there's still 0.25 milliamps, and I'll just go through D1. For
D1. And D1, we assume it's conducting. Okay. Yeah, so that's good. Because ID1 will be I1 minus I2 using the nodal analysis. Which is okay. D1, because we assume D1 is conducting, D1 is forward. So therefore, it can have current going from its P node to the N node, which is fine. So at this point, you're done, or we're done with the circuit, because our assumption is correct. We don't have to go further. Now, of course, yeah, go ahead.
D1, is that ground form?
D1 what? No, the D1 is when it's ideal diode, when it's conducting, the positive and negative terminal voltage will become the same. But when you look at whether it's conducting or not, initially you will look at the voltage has to be higher on the positive side than the negative side. But now the P node of the diode D1 is 0, and the bottom is also 0, but it has current flowing, so that's okay. Yeah, it's like a short circuit. D2 has 0.5 milliamps, 0.25 milliamps too. So each of the circuit will conduct 0.25 milliamps. Why is it half? Because in the beginning, the diode is decided by other parameters in the circuit. It's not by the diode itself. The current cannot be decided if you don't have any resistance or other things in the circuit. But in this case, the current in D2 is decided by the 12K resistance. And the current in D1 is decided by the rest of the circuit.
Well, my thought was that since there was no resistor on D1,
yeah,
D1 will have a higher current than D2, right?
No, because it's decided by the other circuit. You cannot have more current because it's not. From top and or through D1. All the circuit has to satisfy KCL and KVL. Okay. Yeah.
Do you how VO is 0 volts through D1?
Yeah, when it's conducting, there's no voltage through D1. Yeah, so that's why it's 0. So that is why I want you to just go ahead to look at what happens if it's a piecewise linear model. So we're going to continue. So I'm going to erase this one. So now, I said, our conclusion is okay. You don't have to go further. Now, if you have a doubt, well, did I make the right consumption? Did I make something wrong in the process of calculating? So maybe my assumption was okay, but I might made the wrong calculation. So I want to go back. So you can go back saying, okay, let's assume D1 is reverse and see what happens. If you assume D1 is reverse, and then you would calculate the current, and then you will find, well, it's not possible because once you find the current, VO is 1 volt. You cannot have VO 1 volt, the other one, the N node is 0, but P node is 1. That's impossible. So therefore, you cannot assume D1 is reverse biased. You guys can do the exercise. Now you might also ask, why start with D1? Can I start with D2? Absolutely. There's nothing wrong with starting at D2. So if you start with D2, you assume it's conducting, you calculate the currents, and you look at what happens to D1 and make sure that all the currents, they are consistent. Or you can assume D2 is non-conducting and you do the same circuit analysis, but eventually you'll find, well, only one assumption is correct. The other assumption will be wrong. Okay? You cannot have two assumptions. Okay? So now let's move on to look at circuit time. This is a piecewise linear model, which means VD is 0.7 volts in forward direction. So we can use the same procedure we did. So we're going to assume D1 is on. So again, as I said, on, forward, conducting, they mean the same thing, okay? So if we assume D1 on, how much do we get at VO? Because the piecewise linear model D1 is on, which means VO is 0.7 volts. So now we're going to calculate I1, which is going to be 3 volts minus 0.7 divided by 6K. So it's 2.7 divided by 6. You guys can calculate how much that is. Then we're going to calculate I2 as well. So I2 is 0.7 minus 0.7 minus 3 divided by 12K. So this is very interesting. Students are always confused. Why you have 0.7 minus 0.7, then minus 3? Well, because we always 0.7 that was concluded from or derived from D1 conducting. But D2 is conducting as well. Now you can say, how can you say D2 is conducting? Well, if D1, if VO is 0.7, if D2 is not conducting, there's no current, which means that's impossible. You have the voltage difference between D2 is 0.7 minus 3 is 3.7. So that's not possible. So if we assume D1 is conducting, D2 must be conducting in this case. Therefore, D2 will have also 0.7 volts drop. Therefore, you would have and then divide by 12. So you get this one, you have some current, which is equal to 0.25 milliamps. But this one is more than 0.25 for sure. So it's 2.3 divided by 6. That gives you almost 0.4 milliamps. Okay, so maybe 0.39 milliamps. So then you have ID1 equal to I1 minus I2 equal to like 0.14 milliamps, which is similar to the previous case. It's okay because D1 is supposed to have current. D1, if no current, that will be wrong. So D1 can have current. So therefore, we are done in this case. If we flip again, the circuit like this, this will be 12K. you can start the same thing. So you can assume D1 is on, and therefore you will have VO equal to 0.7, and you have I1 equal to like 3 minus 0.7 divided by 12K. Now it's smaller. It's going to be like a 0. So 2.3 divided by 12 is almost, I don't know, like 0 point something. 0. Well, it's less than 0.2 milliamps. So, and I2, you have 0.7 minus 0.7 minus 3, and minus means plus 3 divided by 6K. So that gives you 0.5 milliamps. So I2 apparently is much larger than I1. We call impossible, which means all assumption is wrong. So in the second circuit, like here, D1 must be off. If D1 is off, so what you're doing is, so D1 must be off. So D1 is off instead on. So D1 is off, we cannot decide VO, so we can calculate current. It's going to be 6 volts minus 0.7 divided by 18 kilo ohms. So in this case, why, like in this equation, well, in this equation we have 0.7 minus 0.7, but why in this equation we have only 6 minus 1 0.7, not 2 0.7? Well, because the current flows through that one diode D2, so we divide 0.7, we find the current, and once you find the current, you can find voltage VO is equal to 3 volts minus I1 times 12K. So that gives you a certain voltage you can find. Okay. So I think it's time is just about right. Yeah, go ahead. Well, 0.7 is a voltage drop on D2. On this one, because we always 0.7. The second one, the voltage across D2 is 0.7. Yeah, when you assume D1 is on, VO is 7 in that case. So in this case, when you assume, we don't know the voltage VO. Okay, we have to calculate. Okay, I apologize for the inconvenience. I mean, for the lost time during the technical issues. But as I said, guys, have questions, you can stay or you can come see me. Okay, we're gonna see you again on Thursday. Yeah, you have a question? Yeah.
You're saying D2 is 12.
Yeah, in that case, calculate the voltage. Yeah, because you have a voltage drop 6. That's it.
Yeah.
Yeah.
Test.